Hi, in this video, we want to take a look at ridge regression. All right, ridge regression is conceptually very similar to regular regression, but there's a twist. Okay, in regular old regression, what we're going to do, we're going to find something called the line of best fit. Well, we're going to find the coefficients for the predictor variables that gives us the least sum of squares residuals. Okay, now that is really good. That's really great as long as I don't have excessive variables involved. If I have variables that shouldn't be in there, or if I have redundant variables, especially redundant variables, I can have some problems with overfitting. Remember, the more variables I have, the more predictor variables I have, the more likely that overfitting I am. Okay, so if I'm going to go through and I do regular linear regression and I have variables that I should have like pulled out, removed, I'm going to have some overfitting problems. Okay, so one tactic will be to go through and remove variables. Another tactic is to come up with a mathematical scheme that makes it so that protects us from overfitting. Ridge regression and lasso regression do this for us. We're going to focus on ridge in this video. Okay, so in ridge regression, all of my variables that I put in are kept. The twist is that we figure out a way to minimize the magnitude of the coefficients so that the data doesn't have the opportunity to overfit. All right, now this is similar to lasso. Lasso does the same thing, except lasso will actually kick out predictor variables by setting the coefficient equal to 0. Ridge regression won't. Now, a lot of people would prefer lasso because of the kicking out of predictor variables. I like ridge for one particular use. When I'm dealing with stakeholders and decision makers that absolutely believe 100% that certain predictor variables need to be in the model, but the data does not support their point of view. All right, so what I've done professionally, I have that stakeholders like, this is super important. I get the data. That variable is not important according to the data I have to work with. I need to build a model. Well, I have to build a model that the stakeholder will buy into, or my model is complete crap. It won't be used. All right, so what I've done in the past is I use ridge regression. What ridge regression did for me is it took those predictor variables that I shouldn't have kept in the model if I was doing regular linear regression, and it squeezed down, it reduced the magnitude of the coefficients so that I didn't care if it was there or not because it was small enough that it wasn't causing problems. It wasn't overfitting. So anytime that you are in a situation where you have to include predictor variables that you feel like should not be included, ridge regression is a good choice. All right, so the examples I'm going to run through is the code is modified from this website, which is accompanying this textbook, An Introduction to Statistical Learning with Applications in R. That is hands down the big book on statistical learning, machine learning in R. This is a huge book. This is an important book. If you haven't read it, read it. It's a good book. The book needs no introduction. I don't know if this is an official website or what. I just found this code, and so I grabbed it. All right, so first thing I'm going to do, of course, if I'm going to be working with data, is I need my data. So I'll go ahead and load it. Now I've reduced the number of digits printed just so that I don't have to look at long strings of numbers. And the ISLR package, Introduction to Statistical Learning with R, that package has the data sets for the book. And we're going to look at the hitters data set, the example that's from the book. All right, and I'm going to call my data set M because I'm going to do a little bit of data prep. So I'll just call it M just for data matrix. Now, I looked through the data before I made the video, and I saw that league, division, and new to the league are two-level variables. So I go ahead and I convert those to zeros and ones. And so in the original data set, they're factors. I go ahead and set it so that it's equal to 1 if it's equal to the second level, 0 if it's equal to the first level. And then I go ahead and I went ahead and I removed all of the rows that had missing values. The only missing value cases were for the target variable. In this example, the target variable is salary. So I just didn't want to have to bother with missing values, so I went ahead and just kicked them out. And since the only missing values were the target variable, imputation is not appropriate. All right, so now I'm going to build an initial model just to kind of see what's going on, show the audience what we've got going on. All right, so what I'm going to do, I'm going to take the GLM net package, generalized linear models net package, the namesake function, and X is going to be all of my predictor variables, which is in my data matrix M, and then my Y is salary. So salary is the target variable. Now this next one, the alpha, this says how much of the model is going to be a ridge model, how much of the model is going to be lasso. All right, so this is a flexible program or a flexible function where I can use actually a combination of ridge and lasso if I so choose. Here, since I'm only focusing on ridge, I said equal to 0. And I'm going to start out with an initial grid of value. This should actually be lambda. I made a mistake, but it doesn't really matter. But if I set lambda equal to particular values, I can have control over what are the penalty terms in controlling the coefficient size. All right, so how this system works is that it applies a penalty to the model when evaluating model fit. If the coefficients, the sum of squares of the coefficients is large, it gets hit with a heavier penalty. And now how much of a penalty? Well, we need to figure that out. And what we're going to do, we're going to range through several different levels of penalty to find the best penalty level. And the amount of penalty to the fitting evaluation is based off of the sum of squares of the coefficients. Now, if I'm doing lasso, it'll be the sum of the absolute value of the coefficients. So ridge, it's the sum of the squares, or the square root of the sum of squares, which equivalent to each other. With ridge, variables never get kicked out of the model. With lasso, variables do get kicked out. All right, so let's take a look at what we got. All right, so we can see that here is the lambda value, and we can see our degrees of freedom. The degrees of freedom is constant because we never kick out any variables. And percent of deviation. And we can see that there's about, what, 100 or so? Yeah. All right, so now let's take a look at the actual coefficients. Now, what's going to happen is that for each one of these 100 lambda values, there's going to be a set of coefficients for each of my predictor variable and the intercept. All right, well, that's an entire matrix of values. And so, it's quite a bit. I thought about showing it in the video. I decided not to. What I'm going to do instead is I'm going to take the values, I'm going to do a little bit of data prep, and I'm going to show you what they look like in terms of lambda. And so here I use a coefficient function to grab what the coefficients are. Remember, I have 100 lambda values, and for each lambda value, I have an intercept and 19 coefficients. And now here I'm just doing, I'm getting it set, grabbing the coefficients and putting it onto a data frame. And I'm going ahead and just name the data frame. And now I'm adding another column to the data frame, which I call lambda. And then I'm reshaping to get tidy data for the purpose of ggplot. All right, so now when I do my ggplot, we can take a look and see what's happening. All right, so what's going on is as the penalty factor gets bigger, we can see that assist comes down in size. We see at bat goes from down low, down high, and then it decreases in size to be super small. C at bat decreases as lambda increases. C hits it decreases. And so we can see that the vast majorities of these in terms of trying to model salary, as the penalty term gets bigger, the coefficient gets smaller and smaller and smaller. Now, something to remember is that the coefficient is never actually equal to 0, even if it's super small. Now, if we round off, it might be 0 up to round off, but when I've done this professionally, I just leave it without doing any rounding like that. That way, when the stakeholder says that they want it in there, I can say, yes, it's in there. It's negligible. You can ignore it, but it's still there. And so one thing you can see, if I see a more steep descent on the magnitude of the coefficient, that indicates to me that that's one that has like less informative value in terms of modeling. All right, so now let's take a look at the sum of the squared coefficients. So here I'm going through and I'm just squaring the coefficients and I add them up. I'm using the t-apply function to do this nice and easy. And then I'm creating a data frame where I have the lambda value and then the sum of the squared coefficients. And then I do my ggplot to take a look. And so here we can see the sum of squares of the coefficients in the ridge model. Now, one thing you'll notice is that the intercept is pretty much dominating what's going on. At a certain point in the model, if we look back up at these coefficients, we can see that all the ones that are actually connected to a variable get super close to 0, but the intercept gets really close. That's probably close to the sample average of the salaries. And so when we look here at this, we can see that things are kind of like stabilizing around the intercept, stabilizing on a constant value. All right, so anytime we're doing a machine learning problem, we want to do cross-validation. All right, so what I'm going to do, I'm going to use the cross-validation function that's in GLMNet. This is very nice. I mean, this is easy peasy lemon squeezy. This takes care of a lot of work for me. All right, so it's cv.glmnet, and this will do cross-validation for me to figure out what is the best lambda value, what is the best penalty value in terms of model fitting. Now, I like repeated cross-validation. That is my personal preference. And usually I actually go with a smaller value than this, but this is like the default, so I just left it. I would probably gone with 2 or 3, but whatever. But I'm doing cross-validation. I'm going to do cross-validation repeated 100 times. And so I'm going to have a different splitting of the data each and every time. After I do this, I need to extract the value. Oh, I need to back up. I'm going to use mean absolute error. I like to use mean absolute error for my modeling because when I talk to stakeholders, I want to be able to say, I want to be able to articulate what is it that do I mean by a good fitting model. If I do something like deviance or I do something like mean squared error, then I have another layer of explanation to talk about, like mean squared error. Or the square root of the mean squared error is even worse. Or like deviance. So I want the stakeholder to focus on my model. I want to give the simplest presentation I can. And if you think about it, mean absolute error is pretty good. You can just say the average error and boom, stakeholders get it, even if they don't have a strong math background. Now, let's go ahead and extract the values. So what I'm going to do, I'm going to go through and I'm going to create a data frame for each of the cross-validation runs. I'm going to grab the lambda, the mean absolute error, and the standard deviation of the mean absolute error for the cross-validation. And I'm going to grab all 100 of the cross-validations, and then I'm going to put it all into one big data set. And that's what I'm doing here. So this function, the lapply, extracts the statistics I want from each of the cross-validation runs. Then the dplyr puts them all into one data set. And then as.dataframe, I don't like tibbles, just personal bias. So I use as.dataframe to get rid of the tibble aspect. And now what I want to do, I want to take a look at this using box plots. So remember, I have 100 estimates of the mean absolute error for each value of lambda. And here are my box plots. Okay, so something I noticed about this is that, I've got, a whole bunch of box plots. And if I'm looking through here, it looks like it's probably skewed to the right. something that would be nice to know, that if I end up just by happenstance working with things, I might end up getting a skewed right aspect on a mean absolute error estimate that I wouldn't have caught if I didn't do repeated cross-validation. And so we can, so where I'm focused on is the median value. And so I can, we can kind of get a feel that somewhere over here is going to be the minimum of the median values. All right, so let's go ahead and grab that. Okay, so what I'm going to do, I'm going to compute the median of the mean absolute error for each of the lambdas with the t-apply function. So here I'm taking the mean absolute error, and then I am, for each lambda value, I grab the mean absolute error, and then I take the median. So it's the median of 100 different numbers, one from each of the cross-validation iterations. And then I use which.min to find the smallest, and I just go ahead and grab it. And so here, up to after round off, it's 12. Now, I ran this a couple times. It seemed to bounce around between like 11 to 14. So, I haven't definitively decided what is the best one. But if I look at that plot, box plots, I can see that they're all kind of like relatively close in that region. So even if I'm a little bit off, I'm probably pretty good anyway. And now I'm going to go ahead, I'm going to build my final model. What I'm going to do is I'm going to take GLM nets, and I'm going to put in my predictor variables, my target variable. I'm saying I want ridge, regression, and I'm going to set lambda equal to that value we just looked at, which was rounded off to 12. In fact, it is 11.8. All right. And so after I do that, I've got my model. I could start doing predictions with it, start using my coefficients for inference. I could do whatever I wanted to do with a linear regression model. And here are my actual coefficients. So I could go through and try to reach an inference about what's going on. Now, something about this is that it's hard to interpret importance of a variable in this format. What I could do if I wanted to improve the interpretation is I could go through, I could rescale my predictor variables, then run this, and it would be easier for me to interpret what are the actual values or what are the importance of each variable. And then that would, that gives me like a ranking of importance. But that's all I got for you. Take care and goodbye.